Hey everyone, and welcome back. So, in our intro, we promised we'd start uncovering the hidden math that's all around us. Well, today, we're diving right in with our very first real-world example, taken straight from the first article in the Explosion of Mathematics. And we're starting with something you probably check every single day, the weather forecast. All right, let's get into it.
Remember this question? It's from the preface of the book, but honestly, it's the question we all asked back in math class, right? But what is it good for? Well, this whole series is our answer to that. And we're not going to hit you with some dry theoretical stuff. Nope. We're going to show you with a super powerful and very real example. You know the scene. Every night on the news, someone's standing in front of a big map, pointing at little suns and rain clouds, telling you if you need a jacket tomorrow. It looks so simple, almost charming, right? But what you're seeing is just the tiniest tip of a colossal iceberg. The simplicity on that screen hides an absolutely mind-boggling amount of complexity. So what is really going on back there? All right, so let's pull back the curtain on the weather report. Yeah, you can forget all that red sky at night, sailor's delight stuff. Today's weather forecasting is a total technological beast. We're talking about a world of supercomputers chewing through mountains of satellite data, all powered by some of the most sophisticated mathematical models on the planet. This isn't just about looking at the sky anymore, it's about calculating the sky. And here is the absolute heart of the problem. It's a simple idea, but it's huge. To predict the future, you first have to perfectly, and I mean as perfectly as possible, describe the present. Before you can even begin to guess what the weather will be like tomorrow, you have to know what the entire atmosphere is doing, everywhere on Earth right this second. And that, well, that's our first massive challenge. So let's talk about modeling the Earth's atmosphere. Just think about that for a second. How in the world do you even start to create a model of something so gigantic, so fluid and continuous? It's not like an engine with a fixed number of gears and pistons that you can just map out. It's this massive, swirling ocean of air that covers everything. And this is where we hit a fundamental wall. The atmosphere is continuous. What that means is that between any 2 points in the air, no matter how close they are, you can always find another point, and another, forever. That's a literal infinity of points, each with its own temperature, its own pressure, you name it. And our most powerful tool, the computer, has one major weakness. It absolutely cannot calculate infinity. So how do you solve an infinite problem with a finite machine? Well, this is where the math gets really, really clever. The solution is this beautiful idea called discretization. Basically, if you can't calculate infinity, you just don't. Instead, you strategically chop up that continuous infinite space into a limited, countable number of pieces. It's this brilliant mathematical trick for making the infinite finite. So how does this actually work in practice? Well, these numerical models basically throw a giant imaginary 3D grid over the entire planet. Picture it, covering everything from the ground all the way up to the edge of space. This grid is made up of millions upon millions of little computational boxes. For each one of those boxes, the computer just calculates an average value for things like wind, temperature, and humidity. And just like that, our impossible, infinite problem becomes a huge but solvable puzzle. Okay, awesome. We've got our grid, our millions of boxes. Problem solved, right? Well, not quite. Now we have to figure out what numbers to put in those boxes to get the whole thing started. And this leads us to our second huge challenge, optimizing that starting point. Because the real-world data we have to start with, it's a mess. I mean, just look at the problem with our initial data. We're pulling in information from everywhere. Weather balloons, satellites, commercial airplanes, ground stations. But it's all different kinds of data, and it's totally uneven. We have tons of data points over land, sure. But what about the middle of the Pacific Ocean? Not so much? On top of all that, every single one of those measurements has its own little errors and uncertainties. It's not a clean snapshot. It's more like a fuzzy, incomplete, chaotic collage of information. So how on earth do you take that chaotic mess and turn it into one single, coherent starting point for your model? You guessed it, with another incredibly brilliant mathematical tool. This one is called variational assimilation. It's a powerful technique with deep roots, owing a lot to brilliant minds like the Russian mathematician Lev Pontryagin and the French School of Mathematics. Okay, so how does this actually work? Here's a cool way to think about it. Imagine you have all the observations from the past 24 hours. That's kind of like having a blurry, glitchy video of what the weather actually did. What the algorithm does is it runs the model forward, sees how wrong its prediction is compared to that real video, and then it rewinds and adjusts the starting point, that very first frame. It does this over and over, tweaking that initial state until running the simulation forward produces a forecast that matches up as closely as possible with all those messy real-world observations. It's an amazing optimization process to find the one best possible start.
All right, so we've chopped up the atmosphere. We've used this incredible assimilation technique to get the best possible starting point. We should be golden, right? So why can't we predict the weather a month from now or a year from now? What's the catch? Well, this brings us to the famous butterfly effect and the fundamental limit of all prediction.
The answer came from a meteorologist named Edward Lorenz back in the 1960s. He was the one who discovered that the atmosphere is, fundamentally, a chaotic system. Now, chaotic here doesn't just mean messy or random. It's a precise mathematical term. It means that the system is unbelievably sensitive to its starting conditions.
And this shows you the devastating result of that sensitivity. Look, even with our amazing assimilation, that best possible starting point isn't perfect. There's still some tiny, microscopic error in there. On day one, it's nothing. But in a chaotic system, that error doesn't stay small. It grows, it doubles, then doubles again, exploding exponentially. By day 4, it's getting significant. By day 7, things are getting shaky. And by about day 10, that tiny initial error has become so enormous that it has completely drowned out the actual forecast. The prediction is basically useless at that point. Now, this brings up a really, really important distinction: the difference between weather and climate. Because of chaos, we can't predict the specific weather, like what will the exact temperature be on this day, more than about 10 days out. But that doesn't mean we can't predict climate. It was Lorenz himself who put it perfectly. Climate is what you expect, weather is what you get. We have no idea what the high temperature will be on, say, July 15th, 50 years from now, but we can make very solid statistical predictions about what the average temperature for the month of July will be. That's the key difference.
Okay, so let's just zoom out for a second here and think about the big picture. What have we really seen today? We've seen how mathematics acts as this essential common language, a powerful toolkit that lets us get a handle on a system as massively complex as our planet's atmosphere. And all these powerful ideas we've just talked about, discretization, data assimilation, understanding chaotic systems, they're not just for your 10-day forecast. They are the absolute bedrock of our most advanced climate models. The ones that have to model not just the air, but the oceans, the ice caps, the forests, the whole shebang, all interacting with each other in incredibly complex ways. So really, that's the bottom line. Mathematics gives us this incredible, rigorous framework for modeling the world around us. It lets us test our theories and make real, quantifiable predictions about systems that are just way too complex to understand any other way, from the weather tomorrow all the way to the climate decades from now.
And this is just our first stop, because the kind of mathematical thinking that lets us forecast a hurricane, believe it or not, it's deeply connected to the math that makes that smartphone in your hand work. And yeah, you guessed it. That's exactly where we're headed next.
So I'll just leave you with this question to think about. The next time you pull up the weather app, I hope you see something different. Not just a little icon of a sun or a cloud, but the ghost of an infinite problem that we figured out how to make finite. I hope you see the result of a chaotic dance of data that was tamed by these incredible algorithms. You'll be seeing a testament to the unbelievable power of mathematics to make sense of our world.
In our next explainer, we're jumping into the second article from the book, going behind the scenes of the mobile phone to uncover the hidden math that makes it all possible. You're not going to want to miss that one, so make sure you follow our channel, Stay Blocks, so you get notified. Thanks so much for joining us, and we'll see you then.